Hi everyone, we are Group 3 and today we are going to discuss graphene, the wonder materials. Here are the content page of our presentation. I'm in charge for the properties part, and for applications, rebuttal, and conclusions will be discussed later on by my groupmates. So let's start off with structure. Here are the structure of both graphite and graphene. As you can see, graphite is a 3D structure, while graphene is 2D. Graphene is a single atomic layer of graphite arranged in a hexagonal lattice. It is sp2 hybridized, with a very thin atomic thickness of 0.345 nanometer. You can consider it as one atom thick. Also, it has strong carbon-carbon bonds with bond length of 0.142 nanometer. So here is the question, why is graphene the wonder? Graphene is known as the material of the future, miraculous material of the 21st century, and world of the Internet of Things. It has numerous useful features that can escalate the growth of advanced technology. Graphene can enhance the robotic field by its self-cooling capacity. Running an AI server produces heat frequently. If it is overheated, the server may worn out. Therefore, graphene helps to cool down it promptly. Although graphene is still in laboratories, there are companies that manufacture and sell graphene. Large companies already working with this material, as is the case of Toshiba. For those who don't know, it is a big company that offers wide range of semiconductor products and making electronic devices. With the use of graphene, battery of smartphone can last for few days because graphene can generate electricity by solar energy, and will probably be the most revolutionized devices by the mass use of graphene. It can also be used to cover the cables that we found inside computer. Also, graphene's flexibility improves the performance of foldable devices. In the coming years, smartphone folding screens will be made entirely with graphene layers. iPhone could possibly roll up and stick behind ears like pencil, indicating how amazing graphene is, and it is the key to bring technology to new extents. It can transport electric currents faster than copper, and is capable of connecting the Internet of Things. So, graphene can cope with increased data flow while interacting with 5G. So, let me explain what properties graphene owned, making it so universal. First, it has unique 2D structure. Before 2004, scientists and researchers believed that 2D compound can't exist due to its thermal instability when it undergoes separation. However, the discovery of isolated single-layer graphene rebuts these statements. CC bonds in graphene are very small, strong enough to prevent thermal fluctuation from destabilizing it. To give a better understanding of sp2 hybridization, it makes the p electrons to form a large moving pi bond electron cloud that flows freely. For mechanical properties, graphene is stiff, which is 200 times stronger than steel. Its tensile strength is 130 gigapascal, and Young's modulus is 1 tetrapascal. Graphene is also stable and elastic. When an external force is applied to graphene, the atomic surface inside is deformed and further bent to offset the external force. Thus, there is no rearrangement and misalignment between the carbon atoms. A stable structure is maintained. It can stretch up to 20% of its original length without breaking. Graphene is also light and thin. It is 100 times lighter than a sheet of paper. When working with such a thin layer, graphene may damage. However, it turns out that graphene repairs itself. A team in UK found that carbon atoms would snap into damaged plates to repair. Also, when metal atoms were round, carbon atom would snap into the edge of damaged holes, forming irregular shape. with hydrocarbons nearby. It also has high optical transparency up to 97.7%, while glass only has around 90%. Light can pass through almost unhindered. It exhibits a thermal conductivity of around 4,000 watts per meter Kelvin, but can go up to 5,000 at room temperature. Because of its strong covalent bonding structure, heat can transfer efficiently between carbon atoms, and that's the reason why it has extremely high melting points. It has low photon scattering rates. That means that photons, which are the quantum of heat that transport heat from hotter regions to cooler regions, can travel long distance without colliding with defects or impurities. Table 1 shows the thermal conductivity of graphene at 300 K. Its thermal conductivity already reached 3000 at a relatively low temperature compared to its melting points. Except high thermal conductivity, it also has high thermal diffusivity. Graphene is able to diffuse heat quickly, as it is good at heating dissipation, which means heat transfer. For electronic properties, graphene is a zero-overlap semi-metal which allows electrons to move freely. By adding other materials, the properties of graphene derivatives can be altered. For instance, if you want the material to be more semiconductive, you can make fluorine-doped graphene. If high catalytic activity is needed, sulfur-doped graphene can be made. It has high mobility also because of its massless direct fermions, which means electron transport is rapid. In Table 2, you can see the electron mobility of graphene is really high. There are two doping ways. First, by substituting heteroatom, which is atoms rather than carbon. In this case, boron and nitrogen can be used. Pros of this method is chemical sensing and absorption can be increased. However, it causes defect by electron. The second method is surface transfer, which is by interacting dopants on graphene surface. It consists of charge transfer between graphene and surface absorbance. For instance, low unoccupied molecular orbital of the absorbance lies lower in energy than the Fermi level of graphene. By referring to Table 3, electrons will flow from graphene to the absorbance, making graphene p-type doped. Its advantage is to preserve graphene structure and electronic properties, but it causes local perturbation in structure.